reality of creating a V8 supercar is about designing, building a product that is unique to each team. You can't just zap around the corner and buy bits for your V8 supercar from your nearest auto parts store. These cars are largely custom built, and the teams put a huge emphasis on growing and protecting their own intellectual property, which is why when you look very carefully beneath the skin, no two Fords or Holdens look alike. For over 3 decades, one of the key suppliers and innovators to the industry has been Harrop Engineering in Melbourne. This high-tech engineering operation provides industry of all kinds with advanced precision engineering capabilities. It never ceases to amaze me how some of the components we use are created. There's literally hundreds of components built to exacting specifications based on strength, weight and lighting. Items, for example, like these brake rotors, or for example this diff housing, and we'll talk a lot about diffs and the components that go in here over the course of the weekend. This is cast and machined here at Harrop's. These wheel nuts, which are captive in the middle of a V8 supercar wheel, made from alloy. This beautiful high tensile strength crankshaft, when you'll be absolutely amazed when you discover how this thing starts its life, and this wonderfully crafted aluminium one-piece V8 supercar brake caliper. Let's have a look in more detail how some of this stuff is created. This is a crankshaft, believe it or not. At least it starts its life out this way. It's a piece of rod that weighs about 87 kilos, and through a series of machining, heat treating and finishing stages, we end up here with a finished crank at about 16.5 kilos, along the way shedding about 70 kilograms. How do we get to this? Well, it all starts with a computer. Using computer-aided design or CAD systems, the component is initially drawn on computer. Weight, balance, dimensions, checked to the finest tolerances. This is all done on a virtual basis. Even stress analysis and fatigue prediction can be simulated. The design coordinates are fed into this massive computer-controlled multi-axis machining centre, and the raw billet is loaded into the machine by Mark, who's the machinist managing the project today, and the machine performs its incredible magic. A week later, we've got a crankshaft. It's remarkable. Here's another great example. Take the humble V8 supercar wheel nut. It starts its life out as aluminium alloy bar, then loaded into this machine. 17 minutes later, finished wheel nut. And here it is with the anodising colour on it. Now, these things have got to be made for safety reasons to very precise tolerances, and I'll show you how they measure that. This is the climate-controlled measuring room at Harrop Engineering. Every race car component must be manufactured to a specific set of dimensions, and in this case, the wheel nut is placed here beneath this ruby-tipped probe to check its measurements against those original plans. Now, there's a tolerance, plus or minus, from those original plans, and if it doesn't comply, it's rejected. The amazing thing about this is it can measure down to a finite accuracy of 1 micron, 1,000th of a millimetre. What is 1,000th of a millimetre? It's very small. See this here that I've plucked out? That's 60 microns, so that's 60 times wider than that thing can actually measure. You can see from the vastness of the shop floor and the size of the building, there's no shortage of capability here. Harrop Engineering also has a state-of-the-art casting facility. Remember earlier I showed you a diff housing? Well, together with a bunch of other V8 supercar specialist components, this is where it's made, and I'll show you how it's made. From a computer-designed component, a pattern is created. A resinous sand mixture is then added to form a mould. These are then assembled ready for casting. At 750 degrees Celsius, molten aluminium alloy is poured into the mould. After cooling, the breakout process reveals a rough casting. To finish off and add strength, the item is heat treated to remove stress, then shot peened, where it's bombarded with tiny stainless steel balls to finish and toughen the surface, and finally machined ready for installation. The summary of all this is advanced design and engineering, like you've just seen, adds up to modern race cars that can be driven just as hard on lap 161 as they were on lap 1, and there's still sufficient freedom in the rules to allow the best teams and their technicians to research and develop their own ideas in pursuit of an advantage over the other guy.